In the last lesson, we defined the logarithm as the inverse of an exponential function. This slide is a quick reminder from that lesson. It shows some properties of a general inverse function and how they apply to a specific example. F of x equals 2 to the x. Graphically, we saw that an inverse function is a mirror image of the original function. So it is that the base 2 logarithm as a function of x is simply 2 to the x reflected about the line y equals x. Lastly, this page of examples was provided to help drive home the point. Take the last row. We know by repeated multiplication that 9 cubed is equal to 729. How about the inverse? In the right column, we see that the base 9 logarithm of 729 is equal to 3. The same idea applies to every other row. Just as we learned that there are laws of exponents, there are also laws of logarithms. You may notice that many of them look very similar to what we've seen before. In fact, we are going to use laws of exponents to show why laws of logarithms are true. If you missed the lesson on laws of exponents, feel free to check it out before continuing in this one. If you've never seen laws of exponents before, I doubt the rest of this lesson will make any sense. The first three are true by definition. They are based on how we defined inverse functions. Therefore, they need no further justification. Let's show why this is true. The logarithm of 1 is equal to 0. This is true for any valid base b. To see why this is true, we use the fact that b to the 0 equals 1. Then plug y equals 1 and x equals 0 into our definition of the logarithm. The result comes out automatically. The base b logarithm of b is equal to 1. Why is this true? This has a similar justification. We know from laws of exponents that any base b raised to the 1 is equal to b. Plug y equals b and x equals 1 into our definition of the logarithm. This result also comes out automatically. How about this rule? The logarithm of a product is the sum of two logarithms. We will use the law of exponents underlined in blue to show why this is true. Make the substitution given in the second line. In the third line, we see a cancellation in purple. This comes back to our definition of inverse functions. B to the base b logarithm is simply equal to the argument. In this case, that is p and q. Lastly, I take the logarithm of the left-hand side and right-hand side. By our definition once again, the base b logarithm cancels with b to a power. In this case, the argument is log p plus log q. To show why the law in red is true, we will use the law in blue that we just proved. Consider the case in which k equals 2. By repeated multiplication, p squared is p times p. We use the last rule we proved to show why this is equal to log p plus log p. This equals 2 times log p. Follow the same reasoning for k equals 3, k equals 4, or any other integer to convince yourself why the general case must be true. The logarithm of a quotient is equal to the difference of two logarithms. This rule is very similar to the one involving products, and it will follow a similar line of reasoning. Use the law of exponents underlined in blue. Make the substitution for m and n. Then cancel b to the log base b. Take the logarithm of both sides, make another cancellation, and then you have your final result. Lastly, we are going to show why the logarithm of 1 over q is equal to the negative logarithm of q. To do that, simply substitute p equals 1 into the law we just proved, which involves quotients. That is underlined in blue for convenient reference. Notice that this is consistent with the rule underlined in green, using k equals negative 1. That's because any number to the negative 1 equals 1 over that number. This was covered in the laws of exponents. I failed to mention this in the lesson pertaining to the laws of exponents, but the best way to learn these rules is to practice them. Whether from a textbook, the internet, or some other source, find yourself a worksheet with problems like this. Practice as much as you need to in order to become proficient with manipulating the laws of logarithms. We have shown the rules are true for the logarithm of any base b. Remember that if b is equal to e, we use the natural logarithm. That is the ln. This is simply a different notation, and I want you to know what it means so you're not caught off guard. The same laws of logarithms apply to base e. These are exactly the same as the ones we saw before. Log b is just replaced by ln, the natural logarithm. Feel free to ask questions in the comment section below. Up next, we will explore how to compute the logarithm using a series expansion. I look forward to seeing you then. Thanks for watching.